Hello everybody, I'm Julian and I will present a mission planning for autonomous UAV planetary exploration and biosignature detection, which is part of my PhD research. The content of this presentation covers a condensed literature review of biosignature detection, planetary exploration using UAVs, and UAV autonomous mission planning, closing with a proposal of a probabilistic-based UAV mission planning and navigation for planetary exploration. Introduction. UAVs, commonly called drones, are now used almost everywhere. It's possible to see applications in ecology, resource monitoring, air quality, farming, just to mention a few. But there's still an open area, planetary exploration. In the literature, it's possible to find several proposals, from fixed-wing to natural-inspired designs. Some of the challenges to explore other planets are totally different environment, the lack of GPS, and the communication restriction that demands great levels of autonomy. It's challenging, however. In this moment, 3 missions are flying towards Mars, and one includes a helicopter. But you could be asking why Mars? Despite interesting geological features, which include the biggest canyon and mountain in the entire solar system, Mars is close compared to other planets. And also, there is a lot of expectations about possible Martian life and ideas such as human colonies there. In the bottom right, it's possible to see a delta in the J0 crater. This crater is the landing site for the NASA Perseverance rover and the Engineering Mars helicopter. These images show us patterns associated with liquid flowing in the surface. Perseverance will look for biosignatures in this ancient lake, but what biosignatures means? Biosignatures are morphological, chemical, or isotropic traces of organisms preserving minerals, sediments, and rocks. But how biosignature looks like? Here, we have an example of stromatolites, a mesoscale biosignature alive on Earth. It is formed by cyanobacteria that grow layer by layer on Earth. Still possible to find fossils of stromatolites as old as the life itself on Earth. On Mars, the next mission are looking for this kind of biosignatures. 2 powerful instruments will be used: the Planetary instrument for X-ray lithochemistry or PIXEL, and Sherlock, or the scanning habitable environments with Raman and luminescence for organics and chemical instrument. Those instruments are compact versions of powerful instruments used on Earth. Despite these instruments are compact, UAV platforms still restricted to lighter instruments, such as small cameras and small sensors. Detecting biosignatures like stromatolites on images from UAVs will make possible to pinpoint the location of other biosignatures, which can be targeted by high-resolution instruments on the Perseverance rover. The main challenges are the environment, the distance, and the limited communication. The environmental conditions include extreme temperatures, thin and toxic atmospheres, radiation, not GPS systems, and a weak magnetic field. The increasing capacity of the instruments collecting more data each time create a bottleneck in the mission planning. All these challenges become worse as far as we go in the solar system and are common to any planetary mission, either with rovers or UAVs. Despite the challenges, several proposals can be found in the literature. This table summarizes the most relevant research available since 2008. The most remarkable works are the Mars helicopter Ingenuity and Dragonfly that are already approved to fly. I will start to talk about autonomous mission planning, covering the levels of autonomy of UAVs, what is UAV mission planning, and finally, what is used to take autonomous decisions in uncertain environments such as Mars. From UAV's autonomy literature, it's possible to identify 5 main levels, including the human-operated, the semi-autonomous, the fully autonomous, the long-duration autonomy, and the size autonomy. The size autonomy level does not require a continuous assistance from Earth to generate a mission plan, sometimes of great value for remote missions. The Curiosity rover is a perfect example of a long-duration autonomy system that has been on Mars for more than 8 years. The Curiosity rover operation contemplates the mission operation process presented here, in which the Earth was always in the loop. That was because each instruction needs to be carefully planned to avoid crash or damage the rover, causing significant dead times between each communication window. To make use of the dead times, a system called HighLevel developed by NASA was presented. This software includes procedures to acquire images, detect targets, extract features, filter and prioritize the targets, and collect more samples. The data of the new place helps the team to plan the next step for the rover. HighLevel is a wonderful example of size autonomy that can be conducted using images collected from UAVs. Essentially, we can be much more efficient by removing humans or Earth from the loop wherever possible. And this is even more true for a UAV that move fast and need to know when to spend more time on something of interest. The engineering helicopter is driven by the state machine presented here. The autonomy of the helicopter is located in the long durational level because the waypoints are sent from Earth through the rover. A way to increase the autonomy in the mission planning and navigation is to use tools to increase the decision-making capability in uncertainty environments. One of the most powerful mathematical frameworks for decision-making is the Markov decision process. This framework allows us to model uncertainty in the execution of actions of a system, but assumes fully observable environment, which is not the case for Mars UAVs, in which the states are not fully observable, because the lack of GPS, the observation issues in sensors, and the environment. In the case of Mars, a generalization of the MDP framework for partially observable environments, or POMDP, could be used. This work presents two proposals of a partially observable Markov decision process of POMDP. One is a high-level mission planning model that is on implementation, and a second one is a POMDP for navigation and target finding, tested in a simulated Mars environment. To develop the autonomous mission planning and navigation framework, this architecture was proposed. Three main blocks drive the system: the mission planning block, the integrity block, and the consistency block. The mission planning block includes the following modules. A, the POMDP mission planning module, which its primary goal is to define the policy or set of actions to be executed in order to maximize the mission goals. B, mission context and report module, responsible for collecting the outputs from modules A, C, and D, format the data, and send it to a ground station. A module C, or mission execution module, which takes information from the biosignature detection module to order the navigation module where to go. And D, a biosignature detection module that detects at different scales possible targets in the map, for example, the biosignatures, and provide information regarding possible places to explore and or inspect. The integrity block estimates the UAV hardware constraints and the health of the system. And the consistency block includes the navigation status and the estimation of the proximity of the UAV to safe landing places. The main goal of the high-level POMDP formulation is to reduce the risk of the mission while it's increasing the area being explored and inspected and the value of the data collected. Having this in mind, we consider each state of the UAV as a tuple ST, I, and C. The ST variable refers to the status of the mission presented in the figure. We use a discrete number between 1 and 6 as follows: 1 for landed, 2 for hovering, 3 for exploring or moving horizontally, 4 to inspecting or moving vertically, 5 for landing, and 6 for the undesired start of crash. This diagram represents the states with circles composed by the ST, I, and C variables. The representation is grouped by the discrete variable status. The landed and crash status are presented in green and red respectively. The arrows indicate a possible transitions after taking an action A, and for simplicity and readability, not all possible actions or transitions are presented. The state variables I and C express the average of the outputs of the modules within the integrity and consistency block respectively. The probability of ending the status crash will depend mostly on the integrity and consistency values. This indicates that as soon as the integrity related to the health and hardware restrictions go down, or the consistency related to the landing options and navigation certainty go down, the probability of end in crash status from any status is higher. On this simulation, we test the probabilistic navigation module that controls the UAV from its initial position to find the biosignature target of the simulated Mars surface without GPS. The actions for navigations are hover, move forward, turn left, turn right, move up, and move down. This action describes set points within the states: forward velocity, lateral velocity, and altitude for the UAV motion controller. The observation contains sources of position estimation from internal sensors, including the IMU and the barometric pressure, as we can see in this video. This system is implemented in the simulated Mars environments. Those are robotic operation system nodes and tools used to integrate the simulation environment. In yellow, the current functions that are being implemented and tested. And in blue, the navigation and mission planning nodes are present. The navigation node is the one used in the simulated environment presented earlier. This is the current output of the code with the states, map, and actions highlighted. A simple map is proposed include 4 targets that emulate the biosignatures. Also, different types of land are proposed. Dangerous in red, safe area in green, for example, to land and fly over, and unexplored in gray, and unknown or undefined in orange. The plan is to grow and connect this mission planning proposal to the navigation and other modules in the coming years. In this slide, we have an ideal planetary exploration UAV. This system includes the following parts: the sensors, the onboard computer, and all the modules required for a UAV to fly. In the dark green block, it's possible to see the modules related to the long-term autonomy. And a commercial platform such as the S500 is used for this development. The S500 platform includes the fundamental modules to fly, but also is flexible enough to include cameras to start testing the mission planning strategy proposed. There is also some work in progress conducted by a master and undergraduate students towards the integration and construction of a QUT version of the Mars helicopter. The plan is to test the UAV autonomous mission planning on the S500 and then in the QUT version of the Mars helicopter, closing the gap between the S500 platform and the Ingenuity helicopter that will fly on Mars. Different flight tests has been conducted, increasing the awareness of the steps and procedures required to fly and collect data with UAVs. Photogrammetry training took place with the objective of being able to collect surface map of extremolite formation in a future visit to Mars-like environment in Western Australia. Finally, I want to thank to the lab team, to the other PhD students, and especially to the supervisory team, to Philip, Fernando, and David. Thanks so much for the attention.